Hello everyone. Very good evening to all of you. Good evening everyone. Good evening. Good evening. So audio and video both are okay. Please type in a chat box. Audio and video both are clear, beta. Audio and video both are clear. So shall we start today's session? Okay, so in last session we discussed about surface tension, correct? Right? In last session we started our discussion on surface tension. So actually what is the surface tension and why surface tension come into picture? What is the surface tension and why surface tension is come into picture? So beta, we know that surface tension come into picture due to imbalance between the cohesive force and the adhesive force, right? Surface tension is come into picture due to imbalance between the cohesive force and the adhesive force, and surface tension is simply tensile force per unit length, right? We already discussed that surface tension is a line force, right? Line force means, right, this force is acting in a line, right, like a UDL, right, like is in strength of material. We discuss about the uniformly distributed load in a similar fashion, right, in a similar manner, right? Surface tension is also a line force, right? So surface tension is a line force. That means it is a you can say it is a force per unit length, right? This force is acting in a particular length, right? So surface tension is a line force and it is acting in a length. And also we discussed about the just 1 minute, na? Just 1 minute. Surface tension. And what is the unit? Tell me, what is the unit? Surface tension. It is a tensile force. It is tensile force per unit length, right? Tensile force per unit length, right? And what is the unit? So that unit is Newton per meter. What is the unit? That unit is Newton per meter. Okay, so can we write in terms, can you write in terms of fundamental dimensions? Can you write in terms of fundamental dimensions? So yes, we can write in terms of fundamental dimensions. So in terms of fundamental dimension, this is ml t minus 2 divided by L. So L and L is cancelled out. So this is mt minus 2, right? Mt minus 2. So this is the surface tension in terms of fundamental dimension, right? Now, surface tension force is a very weak force. We discuss about this surface tension force as compared to other forces, right? As compared to other forces which are acting in a fluid element like pressure force, right? Pressure force, viscous force, right? Gravity force, or you can say body force. So as compared to those forces, surface tension force is a very weak force, right? And also we discuss surface tension is a binary property, right? Surface tension is a binary property. What is the meaning of the binary property? Right? What is the meaning of the binary property? Surface tension not only depends on the fluid, it depends on the surrounding fluid also, right? That's why surface tension is a binary property. It depends on the surrounding fluid also, right? And we also discuss surface tension is defined at the interface of the liquid and the gas, right? Or that means you can define the surface tension at the liquid solid interface also, right? But this is very straightforward. The surface tension is defined at the interface, right? Now, as temperature increases, what happened with the surface tension? As temperature increases, what happened with the surface tension? So as temperature increases, we know that the cohesive force, right, cohesive force decreases, and therefore the surface tension decreases. And also we discuss at the critical point, right? At the critical point, the surface tension value is 0. At the critical point, surface tension value is 0. So can anyone tell me what is the critical point? What is the critical point? We discuss about this also, the critical point. Critical point. What is the critical point? So this is the point, right? At this point, no latent heat is required. At this point, no latent heat is required. No latent heat is required to change the phase. To change the phase. Right? No latent heat is required to change the phase. That is called the critical point, right? And we also discuss in case of the ideal fluid, right? For ideal fluid, what is the surface tension? For ideal fluid, what is the surface tension? That surface tension value is 0. For the ideal fluid, surface tension is 0. Why it is 0? Why it is 0? Surface tension is 0. Why it is 0? Because we know that in case of the ideal fluid, right? In case of the ideal fluid, no cohesive force between the molecules. There is no intermolecular attraction force. There is no cohesive force, right? That's why in case of the ideal fluid, the surface tension value is 0, right? And we already discussed surface tension is defined at the interface, right? Surface tension is defined at the interface, right? So for example, right, if I'm talking about the water air interface, water air interface. So what is the value of surface tension at the water air interface? That is around 0.072 Newton per meter. Correct, na? That is around 0.072 Newton per meter. Right? Similarly, if I am talking about the mercury air interface, so at the mercury air interface, this is around 0.48 Newton per meter. Right? 0.48 Newton per meter. Fine. After that, we discuss about the consequences of surface tension. Right. After that, we discuss about the consequences of the surface tension. So this is the first. There are number of consequences. There are number of examples related to the surface tension. Right. So that first example or first consequence is, right, because of the surface tension, in small insects or mosquitoes, right, can easily walk or stay over a free surface of water. Right. That is a very common example related to the surface tension. Right. Now next, second consequence, because of the surface tension, a small diameter needle, right, a small diameter needle floats in a water if you place this needle very gently, right? And in previous class we also discussed about the diameter of the needle. What is the maximum diameter of the needle to float? What is the maximum diameter? We already calculated, na? Remember, right? We are taking some values and we calculated the maximum diameter of the needle which is required to float this needle. We already calculated this, right? So I hope that part is also clear to you. Next example. Okay, come to the next example. Because of the surface tension, washing of the cloth become easy in a hot water and in presence of the detergent. Right. So what happened? See, because of the surface tension, that washing of the cloths become easy. So just tell me, guys, right? Washing of the cloth is easy in a cold water or in a hot water? The washing of the cloth is easy in hot water or in a cold water? So obviously in a hot water, right? In a hot water and in presence of the detergent. So basically what happened, you know that as the temperature increases, so what happened with the surface tension? So surface tension value decreases. We know that as temperature increases, surface tension value decreases. That means cohesive force decreases. Right? And let us consider, right, in a cloth, this is the dirt particle, right? In cloth, let us consider this is the dirt particle and these are the water particles. Right? So obviously see here that intermolecular attraction force between water particles, is a cohesive force, whereas intermolecular attraction force between the dirt particle and the water particle is the adhesive force. So basically what happened when temperature increases, so that cohesive force between the water molecule decreases, right? Cohesive force between the water molecule, cohesive force between the water molecules decreases, right? And this dirt is move away with the water, right? So as temperature increases, surface tension value decreases. Why it decreases? Because cohesive force decreases. And same thing happen with the detergent also, right? Same thing happen with the detergents also. In presence of the detergent, right? In presence of the detergent, if you use the detergent in presence of detergent, in presence of detergent, in presence of detergent, right? Surface tension value decreases. In presence of the detergent, the surface tension value decreases, and therefore washing of the cloth is easy, or washing of the cloth is good in presence of the hot water and the detergents, right? So this is the next consequence. Come to the next, right? Because of the surface tension, liquid droplets, right? Liquid droplets, tears droplet are in spherical shape, right? Sometime in interviews this question is asked, why liquid droplet, rain droplet, tears droplet is spherical in shape. So rain droplet, liquid droplet, right, or tears droplet are in spherical shape because of the surface tension, So basically what happened, right? Any, you can say any surface, right? You can say any surface, or you can say any object try to minimize its surface area, right? Any object or any droplet, you can say, right, tries to minimize its surface area, right, because of the surface tension. And we know that for a given volume, volume, in which case you will get the minimum surface area, for which geometry you will get the minimum surface area for a given volume. So for given volume, we know that sphere has a minimum surface area, right? That is the reason your liquid droplet, right, rain droplet or tears droplet are in spherical shape, because for a given volume, sphere has a minimum surface area. Is it fine? Now come to the next consequence. See, because of the surface tension, that free surface, right, free surface of the liquid is curved like this, right? If you see here, right, this is the water, and this is the mercury, right? This is the water, this is the mercury. So because of the surface tension, if I'm talking about the water, in case of the water, you will get such kind of free surface. Right? In case of the water, right? And in case of the mercury, you will get such kind of free surface, right? And this is nothing but because of the surface tension. So basically we can say, because of the surface tension, the free surface of the liquid is curved, right, either like this or this, right? So this is for water, and this is for mercury. Or you can say this is for the liquid having wettability property, right? Such kind of free surface you are getting for a liquid having wettability property. And this kind of free surface you are getting in a liquid having non-wettability property. So water having wettability property for a normal surface, right? Water having a wettability property, and for mercury having non-wettability property, right? So in case of the water, you are getting such kind of free surface. In case of the mercury, you are getting such kind of free surface. So beta, what happened? See, because of the surface tension, you are getting such kind of the interface. So basically what happened, the pressure, right? Pressure in this side, pressure, and in this side pressure is not same. Let us consider this pressure is P0, and let us consider this pressure is Pi. In a similar fashion, let us consider this pressure is P naught and this pressure is Pi. Right? Please try to understand this point. This point is a very, very important point, right? If I'm talking about the curved surface, because of the surface tension, that free surface of the liquid is a curved, right? And if I'm talking about the pressure, right? This pressure and this pressure are not same. This pressure and this pressure is not same. This pressure and this pressure is not same. So basically there is a pressure difference across a liquid interface, right? There is a pressure difference across a liquid interface, and that pressure difference we can calculate by using the surface tension concept also, right? So I'm not deriving that one, I'm directly writing, right? I'm directly writing that delta P is equal to Pi minus P naught, or better, that one very very important thing, that concave side pressure is more, concave side pressure is more as compared to the convex side, right? So we can write in this way also, that concave side pressure is more as compared to convex side, right? See here, this is the concave side, this is the concave side, and this is the convex side. So this pressure is more than this pressure. Similarly, this is the concave side, this is the convex side. So concave side pressure is always more as compared to the convex side. Is it clear? Right, so delta P is basically Pi minus P naught, and this delta P is equal to sigma 1 upon Ri plus 1 upon R naught, right? 1 upon Ri plus 1 upon R naught, right? And this is nothing but the, or you can say beta Ri plus R1 plus R2. What is the R1, what is the R2, I will discuss. Right, this Pi minus P naught is equal to sigma into 1 upon R1 plus 1 upon R2. And this equation is called, can anyone tell me what is this equation? Can anyone tell me what is this equation? Because this equation is called Young's Laplace equation. This equation is called Young's Laplace equation. Right, this equation is called Young's Laplace equation. Is it clear? Okay, now see, so what is the R1 and what is the R2? Now, let us consider this interface. Better, let us consider this interface. Right, let us consider this interface. Or just take an example, let us consider this is the free surface, right? And I am focusing in this particular portion. So if you exaggerate this particular portion, then you are getting, if you focus in this particular portion, and if you exaggerate this, you are getting such kind of surface. Fine. Now see here, for this curvature, right? For this curvature, this is the radius of curvature, right? Let us consider this is O1. Let us consider this is the O1, and this is nothing but the R1. And for this one, let us consider this is the radius of curvature. This is the radius of curvature, right? And this is the center. Let us consider this is the O2, right? So this is R1, this is R1, and this is R2. This is R1 and this is R2. And this side, this side pressure is, this side pressure is, this side pressure is Pi, and this side pressure is P naught, right? This side pressure is Pi and this side pressure is P naught. So by using the concept of, surface tension and the equilibrium constant, if you use the surface tension concept and the force equilibrium concept, then easily you can derive this equation. This is the Young's Laplace equation. So again I am writing that delta P is nothing but the Pi minus P naught, right? This is the concave side, pressure minus convex side pressure, or always concave side pressure is more as compared to the convex side pressure. So Pi minus P naught is equal to this is sigma 1 by R1 plus 1 by R2, right? This is very, very important equation. This is the Young's Laplace equation. Young's Laplace equation. Right? So is it clear to everyone? Is it clear to everyone? Is it clear? But I am not performing this derivation. Na? That is not required. I am not performing this derivation. I am directly writing the end expression. So this is the end expression, right? This is the pressure difference. So again I am repeating, this is a very simple, right? Because of the surface tension, the free surface of any liquid is a curve, right? Either it is curved like this or like this, right? In case of the liquid having wettability property, you are getting such kind of interface, and in case of the liquid having non-wettability property, you are getting such kind of interface. But anyways, okay, if you are getting a curved surface, then definitely there is a pressure difference across that interface, right? And what is the pressure difference? The pressure difference is Pi minus P naught. Or always remember, concave side pressure is more as compared to the convex side pressure, right? So we can write Pi minus P naught is equal to sigma into 1 by R1 plus 1 by R2. So that 1 by R1, R1 and R2, this is nothing but the radius of curvature, right? R1 and R2 is nothing but the radius of curvature, and sigma is nothing but the surface tension. Right? R1 and R2 is nothing but the radius of curvature. So if I'm talking about this interface, or if I'm talking about this particular interface, right? This interface, again I am repeating, right? See, I am focusing in this particular portion. And if you exaggerate this particular portion, then you are getting such kind of element, right? So for this interface, this is the radius of curvature, that is the R1, and for this interface, this is the radius of curvature, that is R2. Is it okay? Fine. Now come to the next application. Related to the surface tension. So beta, if you know this Young's Laplace equation, then we can easily calculate the pressure difference in case of the liquid droplet, right? We can easily calculate the pressure difference in case of the liquid droplet. So let us consider, right? Now next topic is the calculation of pressure difference. Next topic is calculation of pressure difference. Calculation of pressure difference. Right? That first one is a liquid droplet. Calculation of pressure difference. A, liquid droplet. right? Liquid droplet. B, soap bubble. Soap bubble. C, third one is a bubble, or I can say air bubble. Air bubble in liquid. Air bubble in liquid. And next one is a cylindrical jet. Next one is a cylindrical jet. Next one is a cylindrical jet. So if you have idea about the Young's Laplace equation, then you can easily calculate the pressure difference in case of the liquid jet, in case of the soap bubble, in case of the air bubble in the liquid, in case of the cylindrical jet. So start with the liquid droplet. Start with the liquid droplet. So liquid droplet. So beta, this is the liquid droplet, right? This is the liquid droplet. This is a liquid droplet. And I want to calculate the pressure difference, right, across the interface. I want to calculate Pi minus P naught. I want to calculate Pi minus P naught. So this is the liquid droplet, right? This is the liquid droplet, and if you draw this liquid droplet here, so beta, this is the liquid droplet. Let us consider this is the liquid droplet, and tell me, this is the liquid droplet, and let us consider the diameter of this liquid droplet is d. Right? Let us consider that diameter of the liquid droplet is d. Okay, so tell me in this particular case, or let us consider capital D. Let us consider capital D. Let us consider capital D. So tell me in case of the liquid droplet, what is the R1 and what is the R2? Right? This is your this is your Young's Laplace equation, delta P. This is nothing but the Pi minus P naught, and this is sigma 1 by R1 plus 1 by R2. Right? 1 by R1 plus 1 by R2. Right? So in case of the spherical, right, the liquid droplet is nothing but the spherical shape. I already discussed. This liquid droplet is nothing but the spherical in shape. So beta, if it is spherical in shape, if it is spherical in shape, so simply we can write now that R1 is equal to R2 is equal to R. We can write now. Tell me. We can write now. Right? Your liquid droplet is spherical in shape. If it is spherical in shape, then simply we can write now that R1 is equal to R, R2 is equal to R. Tell me, yes or no? So inside the pressure is Pi, outside the pressure is P naught. And in case of the liquid droplet, R1 and R2 are same, right? R1 and R2 are same, that is equal to R. So beta, this is Pi minus P naught is equal to sigma 1 by R plus 1 by R. And this is nothing but the 2 sigma by R. This is nothing but the 2 sigma by R. So this is Pi minus P naught. Right? 2 sigma by R. Very, very important. Very, very important. So in case of the liquid droplet, that inside pressure minus outside pressure difference is equal to 2 sigma by R, where R is the radius of the liquid droplet and sigma is the surface tension. Okay, now come to the second. Right, this is the first one. This is the first one, or you can say A. Come to the second one. Let us consider this is B. Now air bubble in the liquid. So this is the air bubble in the liquid. So in case of the air bubble in the liquid, so again, if you see air bubble, if you see beta air bubble na, air bubble in the liquid. Now outside there is a liquid and inside there is a air. Correct na beta? Right? In this particular case, inside there is a liquid, and outside there is a air. Right? that air bubble in the liquid is just opposite to this case, just opposite to this case, right? In this case, inside there is a air, whereas outside there is a liquid, right? And in this side the pressure is, in this side the pressure is Pi, and in the side pressure is P naught. So what is the Pi minus P naught in this case? Pi minus P naught. So beta, again this is equal to, again this air bubble is spherical in shape, right? And air bubble is spherical in shape. So tell me, R1 is equal to R2 is equal to R na? R1 is equal to R2 is equal to R na? R1 is equal to R2 is equal to R na? Tell me, yes or no? Yes, sir. Right. So this is nothing but the, right, you are getting same expression, 1 by R plus 1 by R. So this is nothing but the Pi minus P naught. This is equal to 2 sigma by R. 2 sigma by R. Right. So in both the cases, in case of the liquid droplet, and in case of the air bubble in the liquid, in both the cases you are getting the same mathematical expression, which is 2 sigma by R. Right? And case number B, this case is nothing but the, case number B is nothing but the opposite of case number A. Case number B is opposite of case number A. In case number A, right, inside this droplet, there is a liquid, outside there is a air. Whereas in this case, inside there is a air, outside there is a liquid. So I hope you can understand this. I hope you can understand this. Is it fine? Is it fine? Now come to the case number C. Come to the case number C. Come to the case number C. The case number C is a soap bubble. The case number C is a soap bubble. Case number C is a soap bubble. Soap bubble. So if you draw the soap bubble is like this. Soap bubble is like this. Right? This is the soap bubble. Right? This is the soap bubble. And let us consider this thickness. Right? Let us consider this thickness as T and this diameter as D. Right? The diameter as D. This diameter as D. Right? So this is the soap bubble. Is it fine? Now see, if you see this soap bubble, inside there is a air and outside also there is a air, right? Inside the pressure is Pi, whereas outside the pressure is P naught, right? Again, beta, this is the soap bubble. So in case of the soap bubble also, that R1 is equal to R2 is equal to R only, right? In case of the soap bubble also, that R1 is equal to R2 is equal to R only. Right, the soap bubble is also spherical in shape, na? Fine. Now see, this is a soap bubble. Now beta, if you see here, in the soap bubble case, there are two interfaces. Right, in case of the soap bubble, there are two interfaces. This is the one interface. If you see here, this is the one interface. This is the one interface. This is the another interface. Right, this is the one interface and this is the another interface. So let us consider in this side the pressure is Pm. Right, let us consider in this side the pressure is Pm. So beta, what is my objective? My objective is ultimately calculation of Pi minus P naught. Pi minus P naught. So can we write like this? Pi minus Pm plus Pm minus P naught. Can we write like this? Tell me, yes or no? What is my objective? That ultimately my objective is calculation of Pi minus P naught. So beta, can we write Pi minus Pm, right, plus Pm minus P naught? right? There are two interfaces now, beta. There are two interfaces. This is the one interface, right? This is the one interface. This is the another interface. There are two interfaces. So my objective is calculation of Pi minus P naught. So let us consider, if you see here, right? Let us consider, right? Let us consider this is the interface number 1. This is the interface number 1. In this side the pressure is Pi. In this side pressure is Pm. Right? Now there is another interface. There is another interface. Right? In this side pressure is P naught. So we can write now Pi minus P naught is equal to Pi minus M plus Pm minus P naught, because we know that concave side pressure is more as compared to the convex side. Tell me yes or no? Fine. And also, right? And also, see, in this case, it is sigma 1 by R1 plus 1 by R2. In this case also, this is sigma 1 by R1 plus 1 by R2. Right? And beta, we know that the thickness is very, very small, no? The thickness is very, very small. This thickness, right? If I am writing the D naught, so D naught is nothing but the D plus, right? D naught is nothing but the D plus 2 times of T. We can write in this way, or R naught is equal to that R naught is equal to R plus T. And beta, thickness is very, very small, right? If you are getting a soap bubble, then you can't differentiate this is the inner interface and this is the outer interface. You can't differentiate like this, because thickness is very, very small. And since thickness is very, very small, so we can write that R plus T is approximately equal to R, right? Thickness is very, very small, right? Thickness is very, very small, so we can write R plus T is approximately equal to R. Is it fine now? Now see here, okay, this is spherical in shape, so beta, we know that is spherical in shape, so R1 plus R2 is equal to R. R1 plus R2 is equal to R. And let us consider here I am writing R1 dash plus R2 dash, and this R1 dash plus R2 dash, this R1 dash plus R2 dash, R1 dash is equal to R2 dash, and this is equal to R plus T, right? For the inner surface, R1 is equal to R1 is equal to R2 is equal to R. For inner surface, for inner interface, R1 is equal to R2 is equal to R. Whereas for the outer interface, that R1 dash is equal to R2 dash is equal to R plus T, and since T is very, very small, right, and R plus T is approximately equal to R, so we can write like this, right? So beta, what you are getting? See, this is equal to, this is sigma into 2 by R plus sigma into 2 by R, right? So ultimately this is Pi minus P naught is equal to, right, this is 4 sigma by R. So in case of the soap bubble, this is the pressure difference. This is the Pi minus P naught in case of the soap bubble. Right? Any doubt? Is it clear to everyone? This is the case number C. Any doubt? Tell me fast. Is it clear to everyone? If you have any doubt, please let me know, beta. If you have any doubt, please let me know. Shall we move ahead? Okay. Now come to the next case. case number D. Come to the next case, which is a case number D. Come to the next case, which is a case number D. Case number D. Right? Now case number D, the case number D is a liquid jet. Come to the case number D, the case number D is a liquid jet. So if you see here, the case number D, that is a liquid jet. Case number D, liquid jet. So let us consider this is a liquid jet. So let us consider this much part. This part. Let us consider this part. Right? Let us consider this part. This is your liquid jet. This is your liquid jet. And let us consider this liquid jet having length L and diameter as D. Let us consider this liquid jet having length L and the diameter is D. So if you draw this liquid jet here, so beta, this is your liquid jet. This is the liquid jet. Right? This is the liquid jet. And this liquid jet having diameter D and length is L. Right? This liquid jet having diameter D and length is L. Fine. Now, if you see this liquid jet, in this case, ultimately, what is our ultimate objective? Ultimate objective is calculation of Pi minus P naught. This is our ultimate objective. This is our ultimate objective. So what is the R1 and what is the R2 in this case? What is the R1 and what is the R2 in this case? So beta, if you want to see R1 and R2 in this case, so see, if you want to see R1 and R2 in this case, okay, so this is the one interface, right? This is the one interface, right? And this one is the another. Okay, in this case, this one is the one interface. This is the one interface. This is the one interface and this is the another interface. Right? This is the one interface, this is the one interface and this is the another interface. Please try to understand this. Right? And if I'm talking about this interface, this interface, so what is the radius of curvature, beta? In this case, what is the radius of curvature? The radius of curvature is nothing but the radius of the cylinder only. Right? Radius of the cylinder only. Right? So this is the R1. So let us consider this is the surface number 1 and let us consider this is the surface number 2. Right? This is the interface 1, this is the interface 2. So if I ask you what is the R1, so R1 is equal to, in this case, that R1 is equal to R. Tell me yes or no. R1 is equal to R. Tell me yes or no. What happened with the R2? Tell me, what is the R2? Can anyone tell me? What is the R2? Can anyone tell me what is the R2? So beta, that R2 is equal to, what is the R2? Tell me. Right, for this straight line, what is the R2, beta? That R2 is infinite, na? That R2 is infinite. Right, that R1 is equal to R. This is the interface number 1. So R1 is equal to R and this is the interface number 2. So R2 is equal to infinite because this is a straight line. Yes or no? Okay, so again, by using the Young's Laplace equation, you can easily calculate the delta P. So what is the Young's Laplace equation? That delta P is equal to, this is sigma 1 by R1 plus 1 by R2. Right, now R2 is infinite, so 1 by R2 is 0. R1 is equal to R. So simply you can write this is sigma by R. So this is the pressure difference in air. This is the pressure difference in 4 important cases. The first case is the liquid droplet. The second case is the air bubble in the liquid. right? Third important case is the soap bubble case, and the fourth important case is the liquid jet case, right? So if I summarize these all cases, if I summarize these all cases, if I summarize all these four cases, okay, so one, two, so case and delta P. And what is the delta P? The delta P is Pi minus P naught. Right, now case number one. Case number one, the case number one is liquid droplet. Case number one is liquid droplet. Case number one is a liquid droplet. So in case of the liquid droplet, the delta P is 2 sigma by R. Right? The second case is air bubble. Second case is air bubble in liquid. Second is air bubble in liquid. So air bubble in liquid. So delta P is 2 sigma by R. Right? Third case is soap bubble. Soap bubble. So in case of the soap bubble, what is the delta P? The delta P is 4 sigma by R. Right? Now come to the case number 4, that is a liquid jet. Liquid jet. So in case of liquid jet, what is the delta P? The delta P is sigma by R. Right? So these are the 4 important cases. Is it fine? Is it clear? Right? Is it fine? Is it clear? Fine. Now, beta, you can find out this expression. You can find out these expression, whatever the expression that we are getting from the Young's Laplace equation. The same expression you are getting from the from the equilibrium equations also. Right? From the equilibrium equations also. Right? So basically, in this case, there are two type of forces are acting. One is a resisting force, and second one is a bursting force. Right? Just 1 minute. We are getting this expression. We are getting this expression by using the equilibrium concept also. Here I am using the Young's Laplace equation. Once I derive the Young's Laplace equation, then I am applying this Young's Laplace equation in different cases. Right? You can find this expression by using the equilibrium equations also. Equilibrium equations. Right? The summation fx equal to 0. Right? So let us consider that first case, right? Calculation of delta P, calculation of delta P by using equilibrium equation, by using equilibrium equation, by using equilibrium equation, by using equilibrium equation, by using equilibrium equation. Calculation of delta P, calculation of delta P by using equilibrium equation. Just 1 minute. No? Okay. Calculation of delta P by using the equilibrium equation. Now see here, case number 1 or case number A, right? Liquid droplet liquid droplet or air bubble inside the liquid. In both the cases, you are getting same expression. Air bubble inside the liquid, or air bubble in the liquid. Air bubble in the liquid. Right? Liquid droplet or air bubble in the liquid. Liquid droplet or air bubble in the liquid. In both the cases, you are getting the same expression. Same expression. Fine. So let us consider air bubble in the liquid. So beta, this is your air bubble. Right? This is the air bubble. Inside the pressure is Pi. Outside the pressure is P0. Inside there is a air and outside there is a liquid. In both the cases, you are getting the same result. So I am considering a air bubble, right? Let us consider air bubble in the liquid. Inside the pressure is Pi, outside the pressure is P0. Now, we can find out this expression. We can find out this expression by using the equilibrium equations also, right? So to apply the equilibrium equation, that first you know what are the forces that is acting in particular this air bubble. So what are the forces? The first force is the pressure force. The first force is the pressure force, or you can say, because this pressure force is trying to burst this air bubble, so we can say bursting force also. We can say this pressure force is bursting force also. So this is the first force, bursting force. Right? This force try to burst this air bubble. Right? And against this bursting force, there is a resisting force. That's why this bubble is formed. Now, this bubble is formed. That means there is an equilibrium between the bursting force and the resisting force. So this is the bursting force. So what is the resisting force? What is the resisting force? So resisting force is nothing but the surface tension force. Resisting force is nothing but the surface tension force. Surface tension force, and this surface tension force is nothing but the resisting force. Resisting force. Right? So at equilibrium, what happened? Right? At equilibrium, what happened? At equilibrium, what happened? Obviously, at equilibrium, your bursting force, at equilibrium, that bursting force is equal to resisting force. Tell me yes or no. Beta, tell me yes or no. At the equilibrium, that bursting force is equal to resisting force. Now, I want to see the bursting force and the resisting force. So, if you want to see the bursting force and the resisting force, so what I am doing here, right? Let us cut this air bubble. Right? Without cutting, it is not possible to see these bursting force and the resisting force. So let us cut this air bubble. And if you see this, if you cut this air bubble, then see, it is something like this now. Just 1 minute. It is something like this now. It is something like this. It is something like this. And if you want to see the bursting force, so bursting force, we can write this is delta P multiplied by projected area of this sphere. And what is the projected area? The projected area is nothing but the projected area. So this diameter is the capital D. So what is the projected area? The projected area is nothing but the pi by 4 d square. So this is the bursting force. Right? This is the bursting force, the delta P into pi by 4 d square. This is the bursting force. Now, what is the resisting force? what is the resisting force? So beta, resisting force is acting opposite to this force. So this is the resisting force. Resisting force is due to surface tension. Resisting force is due to surface tension. So surface tension acts at the interface like this. This is the surface tension, sigma, 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 sigma. This is the surface tension, right? And we want to know the surface tension force. This is the surface tension. We want to know the surface tension force. Surface tension force is a resisting force. So surface tension force. So this is the surface tension multiplied by length, right? Surface tension multiplied by length, because surface tension is a line force. We want to calculate the surface tension force. So surface tension multiplied by length. So what is the length? The length where surface tension acts. So what is the length? The length is a perimeter. So we can write this is pi into d. Pi into d. So what you are getting? See, pi cancel out, d cancel out. So ultimately what you are getting, the delta p is equal to, this is the 4 sigma divided by, that is d, or we can write 4 sigma divided by 2 r. So 2 ones are 2 twos are, so this is 2 sigma by r. 2 sigma by r. So this is the delta p. Is it clear? Delta p is equal to pi minus p naught is equal to, this is 2 sigma by r. Is it okay or not? Tell me. Right? So you can find out the delta p by using the equilibrium equation also, by using the concept of summation fx equal to 0 or summation fi equal to 0. Right? Is it okay? So this is the case number A, liquid droplet or air bubble in the liquid. Case number 2. Case number 2 or case number B, you can say. Case number B. Soap bubble. Soap bubble. Soap bubble. Right? Soap bubble. So can you find out the delta P in case of the soap bubble? Can you find out the delta P? Can you find out the delta P in case of the soap bubble? In case of the soap bubble. Can you find out the delta P in case of the soap bubble? Soap bubble. Right, so this is the soap bubble. Right, this is the soap bubble. That inside pressure is Pi, outside the pressure is P naught. Right, so again apply the equilibrium equation. Again apply the equilibrium equation. So at equilibrium, bursting force is equal to resisting force. Bursting force is equal to resisting force. So tell me, what is the bursting force? Tell me what is the bursting force. So bursting force is the, okay, fine, just 1 minute. This diameter is, let us consider, that is d, and this thickness is, let us consider, t. So your Ri is equal to R, whereas R naught is equal to R plus T. And we know that T is very, very small. So we can say this is approximately equal to R. T is small, very small, very, very small. Right? So T, R plus T is approximately equal to R. We are not using Pi pressure instead of delta P. No, ultimately this, see here, ultimately what happened, this, the pressure force, this is the bit of total pressure force. If there is a surface, if there are surfaces like this, if there is a surface like this, and in this side, let us consider the pressure force is P1. Pressure is P1, and in this side the pressure is P2. So if I ask you what is the total pressure force? What is the total pressure force? So the total pressure force is delta P multiplied by area, na? The delta P multiplied by area, now what is the total pressure force? If let us consider there is a surface like this, in this side pressure P1 is acting, in this side pressure P2 is acting. So if I ask you what is the total pressure force on this particular element, so what is the pressure force? Tell me. The delta P into pi by delta P into area, na? That is the same thing. Is it fine? Okay. Okay, now, so at equilibrium, bursting force. So what is your bursting force? So again, I am writing directly that bursting force is equal to, this is delta P multiplied by, this is pi by 4 d square. This is the bursting force, beta. This is the bursting force. This is the bursting force. See, this is the bursting force. If you cut section, if you cut section, if you cut section like this, if you cut section like this, and if you draw free body diagram, if you draw free body diagram, so your free body diagram is like this. Your free body diagram is like this. Your free body diagram is like this. Yes or no? If you cut section here, and if you draw free body diagram, so your free body diagram is like this, and the pressure force is delta P multiplied by pi by 4 d square. This is the pressure force. This is the pressure force and resisting force. So if you see the resisting force, so first it is sigma into, beta, first it is, this is equal to sigma into pi di, or simply we can say pi d plus this is the surface tension force. This is the surface tension force acting or at this interface. Now there is another interface also now. See, right? So another surface tension force. So we can write this is sigma into pi d plus 2 times of t, right? Pi into d plus 2t, and we know that d plus 2t is approximately equal to d. So this is sigma pi d plus sigma pi d. So this is 2 sig, sorry, this is, yes, this is 2 sigma pi d, 2 sigma pi d. So this is delta P is equal to delta P into pi by 4 d square is equal to 2 sigma pi d, right? Now this d cancel out, pi cancel out. So ultimately what you are getting, delta P is equal to, this is 8 sigma by d, or you can write 8 sigma by 2r. So 2 ones are 2 fours are. So ultimately the delta P is equal to, this is 4 sigma by r, right? This is the delta P, right? This is the delta P. This is the 4 sigma by r. Fine. Now in case of the cylindrical jet, can you find out in case of the cylindrical jet? In case of the cylindrical jet, can you find out? In case of cylindrical jet, in case of the cylindrical jet, can you find out? Okay. So take 2 to 3 minutes and try for the cylindrical jet by using the equilibrium equation. By using the equilibrium equation, try for cylindrical jet. Calculate delta P for cylindrical jet by using the equilibrium equation. So this is a cylindrical jet. This is the cylindrical jet. Cylindrical jet. This is the cylindrical jet. So this is the diameter D and this is the length L. Fine. So again, inside the pressure is Pi, outside the pressure is P naught. Inside the pressure is Pi, outside the pressure is P naught. And at equilibrium, bursting force is equal to resisting force. Bursting force is equal to resisting force. Now tell me what is the bursting force? Tell me what is the bursting force? That bursting force is equal to, the bursting force is due to pressure difference, delta P. So again, if you want to see the bursting force and the resisting force, so first you cut this section like this. Let us consider this is the x-axis, right? And if I draw the free body diagram, so see here. Okay, it is something like this. So to calculate delta P, so beta delta P multiplied by projected area, right? Delta P multiplied by projected area. Here also we are taking the projected area, na? Here also we are taking the projected area. The pi by 4 d square is the projected area. In the same manner, we can easily take the projected area, na? So the projected area is d multiplied by L, right? This is the d and this is L. Okay, so delta P multiplied by projected area. So tell me what is the projected area? Rectangle area. The projection of cylinder is rectangle, na? Projection of cylinder is, or semi-cylinder is rectangle. So d multiplied by L into. Now resisting force. So beta resisting force, see the resisting force. This is sigma multiplied by L, plus sigma multiplied by L, right? So sigma multiplied by L plus sigma multiplied by L. So this is 2 sigma L. So this is delta P into D into L is equal to, this is 2 sigma L. L and L is cancel out, and this is delta P, and this is 2 sigma by D, and D is 2R. So 2R. So 2 and 2 is cancel out, so this is sigma by R. So Pi minus P naught is equal to delta P is equal to sigma by R. Right? So this is the delta P in case of the cylindrical jet. Is it okay? Is it clear? Is it clear or not? Is it clear or not? It is acting like this, na beta. It is acting like this, na, acting like this. Sigma is acting like this. See, I am showing like this, but actually it is acting like this, perpendicular to the monitor. It is acting like this, like this. So sigma into L plus sigma into L. So it is 2 times of sigma L. Fine. Okay. Now come to the next concept, and that concept is surface energy concept. Right? We can define the surface tension in another form also. Right? We can define the surface tension in another form also. And what is the definition of the surface tension? Surface tension is also defined. Surface tension is also defined as the work required to increase the surface area. Work required to increase the surface area. We can define the surface tension in this way also, right? Or in terms of simple, surface tension is the surface energy per unit area. Surface tension, we can define surface tension in this way also. Surface tension is surface energy per unit area, right? And surface energy is denoted by joule. Energy is denoted by joule and area is denoted by meter square. So beta, this is the another unit of the surface tension, joule per meter square, right? This is the another unit of the surface tension. Surface tension is the joule. Surface tension is also defined as the surface energy per unit area. And what is the unit? That unit is joule per meter square, right? So it is Newton per meter only, right? It is Newton per meter only. It is Newton per meter only. If you are multiplying with meter in the denominator and the numerator, if you multiplying with meter in numerator and denominator, so Newton meter, that Newton meter is nothing but the joule, and meter multiplied by meter is nothing but the meter square, right? So joule per meter square is nothing but the Newton per meter only. Joule per meter square is nothing but the Newton per meter only. Is it fine, right? So we can define surface tension in this form also, surface energy per unit area. But actually, what is the surface energy? What is the surface energy? So beta, what is the surface energy? Okay, so to increase the surface area of a liquid, right? To increase the surface area of a liquid, work is done against the cohesive force of the liquid molecules, right? Or you can say in another way also, right? To form a surface, work is required. To form a surface, work is required, and that work is stored in that particular surface in a form of surface energy, right? To form a surface, that energy is required, work is required, no beta, work is required, right? If you want to blow a soap bubble, if you want to blow a soap bubble, then work is required or not? Tell me. Work is required or not? Tell me. If you want to form a soap bubble, right? Let us consider there is a soap solution. Let us consider there is a soap solution, and from that soap solution, let us consider we want to blow a soap bubble. We want to form a soap bubble from the soap solution. So definitely, bit of work is required, right? So that work or that energy, whatever the energy that we are giving, that is nothing but the surface energy only, right? Now same thing, right? If you want to increase the surface area, or if you want to create a surface area of a liquid, then definitely work is required against the cohesive force of the liquid molecules, and that particular work is stored in the form of surface energy. Is it fine, right? So this work is stored in molecules in the form of the energy that is called the surface energy. So I hope you can understand this, right? So we can define surface tension in another way also. That is nothing but the surface energy per unit area. And what is the unit? That joule per meter square, and joule per meter square is nothing but the Newton per meter only. If you want to write in terms of the fundamental dimension, so it is mt minus 2 only, mt minus 2 only in terms of the fundamental dimensions. Fine. Now to understand this, let us consider there is a U-shaped wire. Let us consider there is a U-shaped wire. Let us consider there is a U-shaped wire like this. U-shaped wire like this. Right? Let us consider U-shaped wire like this. And what I am doing here, I am putting a movable wire here. This is the movable wire, right? This wire is the movable wire. This is the movable wire. this wire can move. This is the movable wire, right? Movable wire, right? And let us consider this dimension as L. Let us consider this dimension as L, right? And this is the initial position of the, this is the initial position of the wire, movable wire. This is the initial position. Now what I'm doing here, right? I'm deeping this particular portion in a, let us consider soap, there is a soap solution. Now I'm putting this particular portion in a soap solution. But then what happened? Tell me what happened. What is the next position of the movable wire? What is the next position of the movable wire? So if you put this particular portion in a soap solution, then what happened? See, then what happened? So again, this is your U-shaped wire. Okay, so this is your U-shaped wire, and this is the initial position of the movable wire. Now what is the final position when you are putting in a soap solution? Then this is the position, this is the position, fine. And this is the better soap solution. This is the soap solution. This is the soap solution, right? This is the soap solution, fine. Now this is the initial position, or you can say position number 1. This is the position number 1, and this is the position number 2, fine. This is the position number 1, and this is the position number 2. So actually this movable wire moves a distance. Let us consider this distance is the ds. Let us consider this is the ds. Fine. Now I want to pull this movable wire to its initial position. That means position number 1, right? I want to pull back this movable wire. I want to pull back this movable wire to position number 1. So for this I am applying a force, right? I am applying a force, and let us consider this force is a F. Let us consider this force is a F. So beta, can you find out the work done? Can you find out the work done which is required to pull the wire from state number 2 to state number 1? Can you find out the work done? Can you find out the work done? Can you find out the work done required? Can you find out the work done required to pull the wire from position 2 to position 1? From position 2 to position 1? Tell me. Can you find out the work done? Can you find out the work done? Better tell me yes or no. Can we find out the work done? Yes, it is absolutely correct, beta. This is F multiplied by ds, and this is equal to. Now, can we write now this F is nothing but the, right? This F, this is the force that I am applying, and beta, this F is nothing but the this F is also equal to, at the equilibrium position, at the equilibrium condition, at equilibrium, this F is equal to the surface tension force. This F is equal to the surface tension force, yes or no? Tell me. This F is equal to the surface tension force, yes or no? Tell me yes or no. Yes, absolutely. This F is equal to surface tension force, which is sigma multiplied by L. Which is sigma multiplied by L. Is it fine? Is it okay? Now, F multiplied by ds. So F is nothing but the beta sigma multiplied by L into ds, right? And this L into ds, L into ds is nothing but the delta A. This is nothing but the sigma multiplied by delta A. Sigma multiplied by delta A, or you can say dA, delta A. Change in the area. Change in the area. Right? So work done against the cohesive force, you can say. Work done against the cohesive force, you can say. Against the cohesive force of the liquid molecules. Or you can say this is the work required to pull the wire. Right? This is W is equal to, this is sigma multiplied by delta A. So you can define sigma from here. This is nothing but the W divided by delta A. W divided by delta A. So surface tension you can define it another way. It is the work required to increase the surface area. Work required to increase the surface area, that is also equal to the surface tension. Is it okay or not? Tell me. Is it okay or not? If it is okay, right? If it is okay, then can we find out the work required for splitting a liquid droplet of radius capital R into n number of small droplets? Can you calculate the work required for splitting a liquid droplet of radius capital R into small droplets, small n number of droplets? So let us consider this is the liquid droplet. Let us consider this is the liquid droplet. Let us consider this is the liquid droplet, and this liquid droplet, let us consider this radius is capital R. This is the liquid droplet. I want to split this liquid droplet into n number of small droplets, n number of small droplets, n number of small droplets, like this. N number of small droplets. What is this process? Can anyone tell me what is the name of this process? Can anyone tell me what is the name of the process where a bigger droplet is splitted into number of n number of bigger droplet is splitted in a number of small droplets? What is that process? Can anyone tell me? So n is the number of small droplets. Small droplets. Can anyone tell me? Can anyone tell me what is the process? What is the name of that process? What is the name of that process? Better, that is atomization. That process is the atomization. That process is the atomization. In an atomization, a bigger droplet. Very good, Praveen. Very good, beta. In atomization process, a bigger droplet is splitted into number of small droplets. So that process is the atomization, right? So let us consider n is the number of small droplets. So can we find out the work which is required to split this droplet into n number of small droplets? So yes, we can find out. We already discussed that work done is equal to this is a surface tension multiplied by delta A. Just 1 minute, na? Just 1 minute. Work done is equal to this is surface tension multiplied by increase in surface area. Right? Sigma multiplied by increase in surface area. Fine. So sigma multiplied by. Now, tell me what is the surface area of this small droplets? What is the surface area of this small droplets? What is the surface area of this small droplets? So let us consider one droplet. What is the surface area of one droplet? So simple, this is 4 pi r square. 4 pi r square. And what is the beta small r? That small r is radius of a small droplet. Radius of a small droplet. Right? So surface area of one droplet is, surface area of one small droplet is 4 pi into r square. And there are n number of droplets. There are n number of droplets. So this is n multiplied by 4 pi r square minus, right? This is the total surface area of this n number of small droplets. And what is the surface area of this bigger droplet? So this is nothing but the 4 pi capital R square, right? So this is the work done which is required, for this particular process, right? Sigma multiplied by n into 4 pi r square minus 4 pi capital R square. Fine. Now, can you find out, right? Can you find out the work done which is required for this process in terms of the given parameters? And what are the given parameters? Given parameter is a capital R. Given parameter is a number of small droplets. So can you find out this expression or work done which is required for this process in terms of the given parameter? Yes, we can find out. So for this, let us consider this is equation number 1, right? And beta, we know that mass is conserved, na? We know that mass is conserved. We know that mass is conserved, right? So mass of this droplet, mass of this bigger droplet is equal to mass of this n number of droplets. So mass is conserved. So we know that mass is conserved. Since mass is conserved, and beta, since mass is conserved, so mass is conserved, m bigger droplet, I am writing like this, bigger droplet, mass of bigger droplet is equal to n multiplied by mass of a smaller droplet, right? That mass of bigger droplet multiplied by n multiplied by mass of a smaller droplet. Fine, na? So what is the mass? We know that density is equal to mass per unit volume. So mass is equal to density multiplied by volume. So we can write in this way also, right? So density, right? Density is cancelled out because density is a, right, intensive property or extensive property, right? It is an intensive property. So whatever the density of this bigger droplet, same density is for the smaller droplet also. So density is same. So simply we can write volume of bigger droplet multiplied by n volume of smaller droplet, right? So what is the volume of bigger droplet? This is 4 by 3 pi r cube. What is the volume of smaller droplet? N. This is n multiplied by, this is 4 by 3 pi small r cube, right? So 4 by 3 cancel out, pi cancel out, right? And small r is equal to r, right? Just 1 minute. Small r, you can write that small r cube is equal to capital R cube divided by n. So from here, that small r is equal to r divided by n to the power 1 by 3. Right? Small r is equal to capital R upon n to the power 1 by 3. Fine. Now put a small r value from equation 1. From equations 1. So work done required is equal to, right, sigma multiplied by n into 4 pi r square. So do one thing, take 4 pi common. Take 4 pi as common. So this is sigma into 4 pi n into r square. So this is r n to the power 1 by 3 square minus minus r square. Right, now this is sigma into 4 pi r square, 4 pi r square into, right, n to the power 1 minus 2 by 3. So n to the power 1 minus 2 by 3, 1 minus 2 by 3. So this is 1 by 3. Correct, na? 1 minus 2 by 3. 1 minus 2 by 3. So this is 1 by 3. So n to the power 1 by 3 minus 1. Right? So this is the work done. This is the work done which is required in this atomization process. Right? Sigma into 4 pi r square n to the power 1 by 3 minus 1, or you can write in this way. This is equal to W is equal to, this is surface area of, right, this is sigma multiplied by surface area of bigger droplet n to the power 1 by 3 minus 1. Right, this is the work done. Fine, is it clear to everyone? Tell me, is it clear or not? Is it clear or not? Tell me. Is it clear? Fine. So problem based on the surface tension, and also I shared some assignment problem now. Are you guys tried or not? Are you guys tried or not? I already shared the assignment problem. So if you have any doubt in assignment problem, you can ask me in next class. Right? So in next class, we discuss problem based on the surface tension, and also we will discuss next property, which is the capillarity. Right? So in the next class, we will discuss those parts. Okay, so thank you so much, guys. Bye bye, take care, and good night, everyone. Good night.